Section 10.3 is Parametric Equations and Calculus. So one of the first things that you've done in calculus, not the first, but one of the early things that you do in Calc 1 is you learn how to find derivatives, right? Yep, you do. So that's where we're actually going to next turn our attention in parametric equations is derivatives, followed very quickly by a couple of applications of antiderivatives. So to start with, in Calc 1, we learned how to calculate the slope of y equal f of x. We'd like to do the same for plane curves. And in that vein, let me introduce you to how we would do that. Theorem 10.7, which is the parametric.
What is the title of the section again?
What's that? It's Parametric Equations and Calculus.
Thank you.
You bet. This is parametric form of the derivative. If a smooth curve, you'll remember that was one of our conditions with Calculus 1 as well. If a smooth curve, C, is given by x equals f of t and y equals g of t, then the slope of C at a point x, y is dy dx equals x prime of t over y prime of t. I wrote that backwards, sorry. It's y over x is obviously y prime of t over x prime of t. There we go. Of course, the condition is that y prime of t can't be 0. I just did it wrong again. I don't know why my notes, well, the problem is that I use different notation, and I like this notation better, so yeah. So, in order to find the derivative, we find two derivatives and we divide them. That's what this says. Okay? So we're going to give it a try. Really straightforward one to start with. Find, and this is dy dx, and our equations, are x equal t squared and y equals 7 minus 6t. So, first things first, what's x prime? 2t. What's y prime? Negative 6. So what is dy dx? Negative 6 over 2t, which reduces to negative 3 over t. Right? Yeah. Yeah. Okay, so like the nuts and bolts of this is nothing new. Absolutely nothing that you haven't seen before. Okay, let's do one more example and then we'll stop for today. One that's just slightly more interesting because it's not quite so clean of answers. That's all we had to do on that particular problem. This next problem, we're going to find several things. We're going to find dy dx. We're going to find the second derivative of y with respect to x twice. and the slope and concavity at the given parameter value. What was that?
We'll just end up plugging that in.
Yes,
Okay.
we will. And because it's fun, we're going to do some with a little bit of trig. X is cosine of 2t, and y is sine of 4t. And the t value, which we're going to look at, is pi over 4. So, to start with, having our first and second derivative are going to be necessary. So what is the first derivative of x? Negative 2 sine of 2t, right. And I'm going to do a second derivative anyway, so let's just, do it now. What would be the second derivative for x? Negative 4 cosine 2t. Now let's do it for y. What's the derivative for y? 4 cosine 4t. And then the second derivative for y? Negative 16.
Oh, gotcha.
It's okay. Negative 16 sine 4t. Okay, so those are the nuts and bolts that we need to put things together. So dy dx would be 4 cosine 4t over 2 negative 2 sine 2t. Because the angles don't match, that's not going to be cotangent, right? The angles do not match. But the 4 and the negative 2 could simplify. So if you prefer, we can go ahead at least to write this as negative 2 cosine 4t over sine 2t. It says to do it at the given parameter. So if we evaluate this at t equals pi over 4, we were to plug that in. I'm not going to belabor the point because I know you guys want your tests back, but if you do plug that in, you actually will get the value of 2. Okay? So that is the slope, right? It said find dy dx, which we did, and then find the slope at the given parameter. That's 2. That's answering 2 of the 4 questions. Second derivative, so d2y over dx2. This one would be negative 16 sine 4t over negative 4 cosine 2t. So the negative 16 and the negative 4 will simplify to 4 sine 4t over cosine 2t. That's the d2y dx2. And then evaluating it at x equals pi over 4, not x, t equals pi over 4. We run into a problem. The problem that we're going to run into is we actually end up with a 0 in the denominator because the cosine of pi over 2 is actually 0. So when we do this, we end up with something on top that's not 0, some number over 0, and of course that's undefined, right? And if you were to graph this, we'll do that next time as we begin, you actually see that you have a curve. This is a very interesting one, the most interesting we've seen because it isn't just mimicking something we did in rectangular coordinates. I'm sure I'm not going to get it drawn quite right, but it looks something like a bow tie. Okay, it's a pretty cool thing because you can't do that in rectangular coordinates, right? We don't have that ability. And so if you're looking at pi over 4, you're actually looking at finding your slope value right here. I was trying to get another color for it.
That's the answer. Undefined.
Yeah, you get an undefined slope, an undefined concavity, I should say it that way. It's not a curve. It's actually not got no concavity right there. Okay, so you saw it happen, in Calculus 2 and Calculus 1 at some different points, but it definitely still can happen when we're working with parametric equations.
Wait, so that makes the concavity
Remember, concavity is simply the curvature. Is it concave up or concave down? If I get a 0 in the denominator, I don't have any, there is no value, so it's undefined. So there's no concavity. So it's undefined concavity, or you could say no concavity would be appropriate. It's just there isn't a concavity at that particular point. Okay?
I have a question about like the notation. So you
Yeah.
have D and then to the 2y and then it's different.
It is different on bottom. And if you go back to your Calc 2 stuff, you'll see that you, or even Calc 1, that's notation that's used there as well. The way we are supposed to read it is it's the second derivative of y with respect to x twice. And that's why the 2's are in different locations. It's the second derivative on top, so that's the D2, and we're doing it with respect to x twice, which is why the 2's after the x on bottom. Yeah, it's not anything new. It's not a notation we use very frequently. It's very nice here, though, to see the slope values and be able to plug them in because we're dealing with two equations and ratios. So we're going to use that. All right, we'll finish this one on Friday.